Welcome to introducing Neo4j 3.1, the Graph Foundation for the Enterprise. We have a great group of panelists from Neo joining us today. Let me just introduce everyone that will be speaking throughout today's event. We have Emil Eifrem, CEO and co-creator of Neo4j. Also joining us from the London office is Jim Weber, Chief Scientist here at Neo. From San Mateo, we have Philip Rathley, VP of Products at Neo. Also Igor Boroyevich, Director of Product Management. And Alistair Green, also Director of Product Management, also joining from London. And then finally myself, Will Lyon, on the Developer Relations team. So here's our agenda for today. As Corey said, we want to make sure this is an interactive event. So we'll be taking questions throughout the sessions here, specifically in the two technical deep dive sessions on the new 3.1 features. And then again, at the end, we have a special fireside chat session where we will open up to the whole panel for questions. And so first, to kick things off, let me introduce Emil, our CEO, who will be giving the welcome and the overview. And so with that, over to you, Emil.
Thanks, Will, and welcome everyone to this live launch of Neo4j 3.1. It's mid-December, so I'll use this opportunity to wish everyone an early happy holiday and early happy new year. 2016 has been a fantastic year for us here at Neo. I'm usually based in Silicon Valley, but I'm actually in London today. And I guess about 6 months ago, early this spring, we had our user conference Graph Connect here in London, where we had over 700 people at the conference. It was a fantastic show when we launched Neo4j 3.0. And 6 months later, in San Francisco, we announced the beta of Neo4j 3.1, where we had 1,400 people registered, over 1,000 people in the actual conference. Today, we have over 200 customers at Neo4j and over tens of thousands of deployments. One of the biggest things I think that happened to us in the graph space this year was something that probably most of you have heard of, which is the Panama Papers. It made, I think, more of a splash here in Europe than it did in America, but it was one of the biggest stories, if not the biggest story, for several weeks this spring. And basically, it is the biggest data leak in journalistic history. So there was a law firm that was specialized in tax planning that got a lot of documents leaked. And they were analyzed by an association of journalists, over 200 journalists collaborating under the Consortium of Investigative Journalists, ICIJ. And it had a huge impact. There was information about all kinds of politicians. For example, the Prime Minister of Iceland ended up resigning over findings in the Panama Papers. So a big news flash. And as I mentioned, it turned out to be the biggest leak in journalistic history. If you compare that to some other famous leaks like Edward Snowden or the WikiLeaks, it has hundreds of thousands, sometimes low millions of documents. The Panama Papers had over 11 million documents, which is, I think, a pretty significant number of documents that they managed to analyze. And of course, the underlying technology for all of this was Neo4j, which we're very, very happy and proud about. If we think about that and setting aside anything about technology at all, just conceptually think about what you want to do if you're a journalist and you want to analyze something like tax evasion, right? What you want to do then is probably something like you want to identify individuals, persons with names and things like that, right? They may be connected to bank accounts, which is not a problem. That's what I have. That's what all of us have, right? But what you're looking for is probably not direct connections between an individual and their bank accounts, like is represented in this slide, but something a little bit more vague or a little bit more complex, which is kind of indirect connections. So for example, this person may live at an address, and at that address is another individual who is connected to a company who in turn is registered with a specific bank. This is actually not a hypothetical example. This is the example of that Icelandic prime minister who was not directly connected to an account in a tax haven, but he was indirectly, right? And here, of course, since we're data people and graph people, this is to us the graph, right? And in the graph world, we call these concepts we call nodes and relationships, right? And so if you draw something like this on whiteboard, for example, conceptually you might identify something in a particular domain that you're modeling, but what you're using then in the graph world is nodes and relationships. Right, so we've been able to model this domain in this particular case, which happened to be investigative journalism, right? And it's just concepts, but in the graph world, we call those nodes and relationships. And that's a very powerful model. It's very agile. It's easy to evolve. You can model anything with it, and that's very powerful in and of itself. What's even more powerful is if you can do that at scale, right? So you can do that with whatever 5, 10 nodes is, I guess, the example, all the way up to millions of nodes, or for that matter, billions of nodes or trillions of nodes. And that's when you can get some really powerful applications built. Example of that is, of course, some famous graph applications. Google is maybe the most prominent one. When they entered into the web search game in the late 90s, there were 20 or so search engines out there already, and they all did the same thing. They downloaded the entire internet, which I think was amazing, like the entire web at the time, into their data centers. And then when you search for something like a graph, or you search for something like webinar, it would look inside of each and every one of these documents, right? But Google came along and said, hey, we're going to do that, but on top of that, we're going to analyze these documents, and we're going to look for the links. And those links, we're going to extract them into a connected data structure, and then we're going to rank the search results based on that. So they took that shift and said that, yeah, data in isolation is valuable, but what's even more valuable is data in connections, right? Another example of this is Monster.com and the shift from looking at CVs and job profiles in isolation versus something like LinkedIn, which was able to manage and store and retrieve and work with the relationships between professionals and use that as a way of finding a new job, which ended up being a much more valuable way of doing things. And the final example is actually from the world of online banking, where it used to be, all the traditional banks who went online but had a hard time doing online payments. And the reason for that was that it's very hard to detect fraud if the only thing you can see is, a simple transaction with a from and a to, and then an amount. Whereas PayPal managed to capture the entire payment graph, and then it's a lot easier to detect fraud. So those are some examples of what you can do when you can truly manage graphs at scale. Couple of other use cases, right? So that's been one of the biggest shifts that we've seen in the past probably couple of years, where it used to be that we knew very well that once you had connected data, a graph database was a very good fit, once there was value in managing that data. But how did that actually break down into particular use cases and industries? Well, that was a bit unclear a few years ago. Today, we see a number of use cases that are emerging very clearly as top use cases for graph databases. A very famous one is real-time recommendations, where companies like Walmart use Neo4j to manage products and the relationships to particular customers. So when you go online to a big retailer, you're going to get a recommendation, sometimes based on your purchase history. But since the graph database can leverage data in real time, you can also get recommendations even based on very recent history, like how you've navigated on that site. So that's one example. Fraud detection ends up being very valuable to take a connected data view, so you can detect so-called fraud rings which is very popular in banking, in government. Network and IT operations. Turns out that in a lot of network management in telco and IT operations in general, what you want to do is you want to build up a model of your entire data center or your entire telco network. And then you can do things like, what happens if that cell tower over there blows down? How will that cascade across my telco network? Or if that switch goes down, or if I plug in a new firewall, how's that going to impact my entire network? Master data management ends up having a lot of hierarchical and network-oriented data, be it suppliers and how they're connected through your entire supply chain, or your product hierarchies, or your organization. And when it comes to content and knowledge graphs, a lot of people use graphs to augment and complement existing normal text searching capabilities, much in the way that Google did that on the entire web back in the late 90s. And then finally, the sixth top use case is identity and access management, which ends up being very relationship oriented when you look at this particular individual and how they're connected to all the different assets inside of an organization. So that's one of the biggest things that we've seen happen over the past couple of years, our ability to articulate the value of graph databases for particular verticals and industries and use cases. What's happened more recently, though, is that we've seen a big shift in graph database adoption, where it used to be that we got selected specifically for these particular use cases. But what's been happening more recently is that it's becoming more of an enterprise-wide standard. And that's a very exciting and interesting shift. But the question then is, like, why do we even see this shift? And I thought, in order to answer that, we'd take a little bit of a detour and talk about the let's call it the changing business landscape of 2016. There's this, I think, famous study of the Standard & Poor's 500, the 500 supposedly biggest companies in the US, where some researchers at Yale, they studied this list, and they came to what I think is a fairly mind-blowing conclusion, which is that the average company lifespan in the Standard & Poor's 500 has dropped significantly over the past 50 years. It used to be back in 1960, 65 years. Today it's around 20 years, and it's predicted to drop even further. And in fact, what people predict is that 75% of the Standard & Poor's 500 is going to be replaced in the next 10 years. And that, I think, is pretty mind-blowing. And what is interesting is that I think if you take any list, your own industry's list, and you'll find that the trend is similar, right? So the question then becomes, how do you make sure that your company is one of the ones that survive? How do you stay in that 25%, right? And I'm sure there's a lot of things related to that, but one thing that seems to be a very common conclusion is that there's a lot of value in data, right? We have people saying things like, data is the new oil, like really the growth engine, if you will, of the 21st century. But of course, what we've seen at Neo4j is that it's not enough with data in isolation. The companies that truly drive a sustained competitive advantage are the ones that are also able to use connections in data. And here's the example, of course, of Google. So thinking back then on the 75% of our industry, of your industry, that is going to disappear over the next decade, what can we learn from the Googles of the world? Well, really what Google did is that Google took the data that was core to their business and it connected it, right? That's really what they did. What was the core data for Google? It was all the web pages. And they made sure that they identified all the connections, but not just identified them, they put them in a technology that they were able to, that was able to leverage those connections and use them in real time as they searched the web, right? Now, of course, unfortunately for Google, they had to build that technology stack from the ground up. And fortunately for people today that want to do that, is that there is technology now where you can do this off the shelf. So how we think about this is kind of, we're imagining a world that where your supply chain, your logistics, your manufacturing, your commerce, your payments, your CRM, everything is connected. right? Where every single piece of data can start anywhere, right? And end anywhere, from the supplier to the product to the customer, from the customer through the payment to the product, etc. Where all of these connections are stored, managed, and used, right? And used to run the company, run the business. And we call this the connected enterprise. And we believe that those are the companies that are going to be the 25% winners in their industry. And we see those companies emerge in all kinds of verticals, right? They're completely horizontal phenomena, but we see a lot of them in software, in finance, in retail, in telco, in media, etc. What unifies them are two things. One is that they see this extraordinary value in connections in their data. But the second one is that they're really held back by legacy technologies, right? Let's take retail as an example of that, right? If you look into any big or small retailer today, they may have challenges, but one of them isn't building a front end. If you look at the Amazons of the world and you compare them to any other retailer, like the front end is really looking the same. Their mobile web store look all the same. You can put any student to put that together in a day or two, right? That's not what's differentiating. The UI is simple. What's hard is getting the backend in place and the data in place to be able to deliver on that UI, right? So let's look at, for example, double click on two things on this particular slide, right? Real-time local inventory, right? Okay, so it's very easy to put an icon up on your web, right? But in order to be able to do pickup in store, you need an up-to-date view, a real-time view, really, of your inventory, right? Of every single store where you are, related to that particular user's geography and position, which is pretty significant on the back-end side of things. If you look at real-time recommendations, you need to have your entire purchase history, but in a way, so not just as a huge list of everything you've bought since the 70s, right? When the retailers first started introducing IT systems, but in a format or in a shape so that you can look at your particular individual, how they're connected to various products, how those products are connected to product hierarchies, and then manage that in real time to do recommendations, right? And so what are the challenges with this, right? Well, the challenge is of course, that many of these systems were built with relational databases, and relational databases are amazing. It's a fantastic piece of technology that is useful in a wide variety of situations. But one of the areas where it's not very good is in managing connections, right? So if you have connections in that data set, it's very hard to query that in real time. And not more, even more so than that, connections inside of that data set is very difficult. Connections between data sets are almost impossible, right? And so what we see, though, is customers take one of these legacy systems, let's say products or purchase history or something like that, and then side by side, do they add Neo4j to their architecture? Very important is that they don't replace their existing relational backends. They coexist. But all of a sudden, they can use those relationships in that data, right? And sometimes we see people duplicating, replicating the relationships, right? So they still exist in the existing legacy technology, as well as in Neo4j. Sometimes they move them over. So the isolated data is in a relational database, but the connected data exists only in Neo4j. And sometimes it's a progression. You start out with it replicated in both locations. Once you've run Neo4j for a year or two, you're confident in its abilities. Then you make Neo4j the system of record for the connections, right? And they're able to build maybe a recommendation engine based on that particular thing. And then a while later, they realized, hey, we have the same problem in some other area, right? Maybe it's the supply chain, right? Which ultimately is a chain, which is a big connected data structure. And so then they introduced Neo4j side by side to that, and then maybe 6 months later, they add a third system. And then all of a sudden, they realized that, wait, why would I add a third Neo4j cluster? I might even be able to put my, I don't know, products and my supply chain into the same system. So all of a sudden I can detect that, hey, what if that, truck that is used by my supplier is getting delayed by a day? How will that cascade across my entire supply chain all the way down out into my stores, so that when someone is walking around doing a mobile recommendation, they're not going to get the recommendation for something that won't be in that particular store where they want to pick it up later, right? We think this is an amazingly powerful way of converging towards a more modern architecture, not replacing the relational databases, but the database, but running side by side with it. And then all of a sudden you can build all these new services. I put up a few on the slide: same-day delivery, right, or real-time recommendations, or looking at payments and figure out whether they should accept them. And I'm sure many of these can be built with a relational backend, right? But it's going to be a lot harder. And quite a few of them, you actually physically can't even build them if you're using a relational backend. And so we see this transitioning, of course, from this legacy technology and silos into what we call the connected enterprise. That's not a retail trend. That's a trend that is happening across all industries, right? And here are some examples of those companies that are moving towards being what we call a connected enterprise. Everyone, anywhere from finance to retail to social to telecom to healthcare, right? So we can say a lot of things about the future, but one thing that is clear is that we're moving towards a highly connected one, and that, of course, is the future for which we are building Neo4j. So without further ado, please allow me to pass on the presentership to the head of products for Neo4j, Philip Rathlee.
Great. Welcome, everyone. Great to be here with you. I'm going to give you a quick overview of what's happened in 2016 with Neo4j, which includes today's Neo4j 3.1 launch. And I'm going to start by giving a little bit of a perspective on what the main themes are in 2016. And they cut across three different areas. Number one is performance and scale, but a hallmark of Neo4j that those of you who have not worked with the technology may or may not be aware of it is the efficiency of Neo4j. We often hear from users that not only can you run queries much faster, but you can do so with 1/10 the hardware, 1/5 the hardware, fraction of the hardware that you can with other technologies. So performance and scale with efficiency has been a huge focus throughout this year. Another one is all the development features that make it easier to develop, more convenient to develop. That's another big area. And then the third is operations and security, being able to manage data inside your data center, including all the features that enterprises look for in order to protect your data in this day and age where that's increasingly an important thing. And let's take a step back. I want to put some perspective on the challenge of architecting for connected data, because it requires very different techniques than when you architect for data that's not connected. If you look at the spectrum of connected data on one hand, disconnected data on the other, you can look at Neo4j on one extreme, technologies like Mongo, Cassandra, React, Redis, etc. at the other extreme, and then maybe relational databases are somewhere in the middle. And architecting in such a way that you can scale, if that's the only thing you care about, and you don't care about performance or necessarily about being able to have full trust in your data, then that's a much easier problem. Or I can architect for performance, but then sacrifice the other two. So you can look at this as maybe some kind of equivalent of reflection of the CAP theorem, maybe in a loose way around connected data and the kinds of architectures that you have. With Neo4j, we optimize for all three. And accomplishing all three together is highly non-trivial for connected data problems. And at the heart of this is trust. And as a database,
we've taken a contrarian attitude from the early days. Emil was up on stage back in 2009 at the early NoSQL conferences talking about how ACID is an important thing. Well, it's especially important for graphs where you need to know that a relationship actually lands somewhere and doesn't vanish into nothing. So a value that we've always had is a deep emphasis on reliability and quality. And what that means is that in any given year, whatever features you actually see emerging that you can use are something, akin to the tip of the proverbial iceberg. And underneath that, there is all sorts of work that's happened on the infrastructure side, some of which are visible and some of which may not be so visible in the form of the test infrastructure that the engineering team has built and the many thousands of hours of clusters running and getting smashed apart on large clusters inside of our test environments to make sure things are reliable, trustable, so that when you put Neo4j into production, you can know that your data will be safe. And if you line this up against what we did last year, you can kind of see, that the features represent a small portion of things, and then you've got all these other things which are infrastructure, and these are product areas. It doesn't include the significant improvements that have been made inside of our engineering processes and infrastructure. So let's dive into 2016, looking at these three themes. And I'll start with performance and scale. And actually, to put it into context, let's look at some of the groundwork that was put into place in 2015 to allow and enable the things that we did in 2016. So in 2015, there was a cost-based optimizer that was introduced. This replaced the Cypher rule-based optimizer. And along with that, you got some nifty tooling to give you some introspection into how queries ran and what the optimizer was actually doing. This is a screenshot of that, and that's available as explain and profile functionality in the Neo4j browser across all editions. And the cost-based optimizer makes much smarter choices about how to run Cypher queries using information that's in the graph, that's now gathered under the hood as you update the graph. Number two is moving to a page cache, and the implication there from a scaling perspective is quite significant. That previously Neo4j had some scaling limitations insofar as how large your graph could be, because all of the data in cache was stored on the Java heap. And Java heaps don't particularly behave well, or Java doesn't particularly behave well once I get in, beyond the low to mid tens of gigabytes, which means that if I have a very large graph and I want to run fast in-memory kinds of queries, that can actually put a lot of pressure that shows up in the form of garbage collection, and can cascade into various kinds of problems when you're running a cluster. And so in the 2.3 release, we fully moved off of the on-heap cache onto an off-heap cache, which enables full use of the kinds of memory that's available relatively cheaply now on modern hardware. And then third, there were numerous other improvements. I'm picking on one. These are some improvements that were made to actually unify writes to the graph and the index, which are always kept in sync as part of the the ACID transaction I mentioned. It's not just relationships and nodes; it's also the associated schema indexes, and this, and as well as doing some buffering so that you can, when you have highly concurrent write workloads, Neo4j will automatically commit them in multiple chunks without losing any latency, kind of piggybacking writes atop each other as the writes are committed down to disk. So that's 2015. A bunch of stuff was happening in the background while this was being delivered, and I'm happy that some of it landed in 3.0, and then some of it's landing today in 3.1. So if we look at 2016, one of the features that was announced at Graphic Connect Europe in London in April of this year, in Neo4j 3.0, was support for unlimited size graphs. This was another scalability limitation up until this year, where because of the compromise and the trade-offs between performance and scale, beyond a certain size, you started into the tens of billions of nodes and relationships and properties. You previously saw some compromises in performance, and so we simply chose to not allow graphs to grow larger than that size. If you need something bigger than that size, which is generally the exception, not the rule, then you could use application-based charting or sort of other techniques to manage this. We found a clever way to burst past these limits so that effectively you have no limits, and this leverages something we call dynamic pointer compression. We also do auto-index partitioning, so under the hood, your schema indexes, once they get to more than 2 billion objects, they automatically partition into more indexes. And the great thing about this is it happens without any compromise to performance. We also introduced a binary protocol. This both has some performance advantages, as you might expect. It also has some really important development advantages that I'll get to when we go through that theme. And then last of all, Cypher is the most convenient way to write graph queries. It's not yet the most performant way to write graph queries. Oftentimes Cypher is fast enough. We see many customers who will take the 5% of queries that are running responsible for 95% of the workload, or queries that need that extra little bit of tuning, and drop those down as procedures using the imperative native API available through procedures. So those are accessed through Bolt, and there's been a great community effort. If you look at APOC out in Neo4j Contrib, you'll see hundreds of procedures. There's some great examples, blog posts from the folks at Neo, the dev rel team, and the Neo4j community around what to do with those, with the literally hundreds of procedures that are now out there that you can tap into. So it's also a nice way to package in different kinds of functionality that ranges from pulling data in from relational databases to accessing third-party products, to running graph algorithms, to even doing simple things like creating UUIDs and so on. So these all landed in Neo4j 3.0. So these have been available now for around 6 months, a bit more than that. And there's more. So in 2016, we're now introducing in Neo4j 3.1 an entirely new clustering architecture. This is our 3rd generation clustering architecture. The 1st generation relied on Zookeeper back prior to 2013. Our 2nd generation clustering architecture, which will continue to remain available, so you don't have to move over to causal clustering for the time being. We call that the HA architecture, and that implemented our own Paxos algorithm using master-slave replication. Causal clustering is something entirely new. You'll get a great deep dive into it from Alistair Green, and causal clustering provides all sorts of advantages, including getting beyond this master-slave architecture and some of the limitations that it had. There have been all sorts of improvements in the database engine. Those of you who've used Neo4j for a while may have noticed that in order for empty space created by that's been freed up by deleted nodes and relationships requires a restart of the database in order to be marked available for reclaiming. That now happens online. in the Neo4j Enterprise Edition. We also have reintroduced the execution guard, which allows admins to set a time above which, if a query takes longer than X amount of time, then automatically kill it. This is to protect operational environments from people running long-running ad hoc queries. And then also lots of great improvements in index ingestion performance. And then finally, we are GAing our first hardware acceleration feature in the form of supporting IBM Power8 with CAPI Flash. IBM's got this amazing technology that actually does for I/O what GPUs do for graphics workload, which is to move your I/O processing off to a dedicated coprocessor. They call this CAPI Flash, and it's a feature that's actually taken a couple of years to build towards, and without certain of the improvements I mentioned earlier, it wouldn't be possible, like moving the heap off cache off heap. These are all new to Neo4j 3.1. So that's performance and scale. Let me talk about productivity and convenience, theme number 2. In 2016, we introduced official language drivers. Those are backed by the binary protocol that I mentioned, which is called Bolt. So it's a really nice, convenient, uniform way to develop with Neo4j. And there's now a type system that's uniform across the storage format, Cypher, the drivers, and Bolt. There's a new command line interface that was just released. Also has some nice security benefits in that it supports Bolt and works with all the security features. There's a new schema viewer, which lets you introspect your graph. Interestingly, this uses the same statistics that are used by the cost-based optimizer. And to my knowledge, Neo4j is the only database management system that keeps exact up to the last ACID transaction statistics in the database that allows exact up to the last ACID transaction viewing of schema, as well as, and it's also something that the cost-based optimizer uses under the hood to give you incredibly fast queries for things like counting the number of nodes, counting the number of nodes by label, et cetera. That happens automatically. In April, we announced our first a new Cloud Companion service that offers a Neo4j browser sync feature for keeping my favorite settings and queries in sync across all my different sessions and databases. And last but not least, in addition to procedures, which were launched in 3.0, we're expanding into user-defined functions so that you can use those procedures inline, as you can see here in this create UUID example. So the 3 latter features launch in Neo4j 3.1 today. And then last but not least, operations and security. In 2016, we first of all, in 3.0, took advantage of a new .0 release to actually completely change the way files are structured, configuration is done, and the way logs are handled. We of course included a utility that makes it easy to port over your existing config changes so that you don't need to port those over by hand. And this makes it much easier to run Neo4j across a whole range of environments, including Docker and infrastructure and platform as a service environments. One of the top line features in Neo4j 3.1 is a new security foundation. So a whole set of features that Igor will give you a great deep dive into very shortly. And then last but not least, lots of new sysadmin features, including being able to kill queries across a cluster, including being able to control user access. And then there's a new utility for doing administrative work on the command line for admins. So that's our 2,000-foot overview of what's happened for the year, highlighting what's new in Neo4j 3.1. And next, we'll continue into the deep dive. Thanks.
Great, thank you. So next up we have Alistair Green, Director of Product Management, who will be doing a feature deep dive on the new causal clustering in Neo4j 3.1. Over to you, Alistair.
So I'd like to say hello to everybody on this launch of the new features in Neo4j 3.1. So apologies, I just need to get my slide up properly. Okay, I'm hoping you can see that properly. The feature I'd really like to talk about here is the new evolution of the Neo4j cluster architecture, which we're calling causal clustering. And that name reflects the fact that amongst a number of other advances in the cluster architecture, we're really sort of pursuing the next step in a journey towards a more fully transactional and horizontally scalable architecture over time. And one of the important aspects of that is the introduction of a feature called causal consistency as part of this release. So we already have highly available cluster computing for graph data in Neo4j, Neo4j 3.0. That includes capabilities for distributing workload, for large-scale throughput, for data redundancy, providing fault tolerance, and high availability in terms of support for fault tolerance support for the processing workload. With Neo4j 3.1, we're evolving to the next sort of level in terms of the fault-tolerant graph database. So one of the changes we've introduced is moving from a Paxos-based architecture, which was in fact our second generation cluster architecture, to the Raft protocol. And with that, we maintain the ability to have continuously available server pool or server cluster, but we're also adding consensus commits. So all commit traffic is carried out on a consensus basis by a quorum of servers within a consensus group. And that means that we can deliver a consistently ordered stream of transactions to all of the servers within the cluster, and do so in such a way that it's impossible for there to be any kind of branching or split brain phenomenon. We've also enhanced the drivers and the use of the bulk protocol that Philip referred to avoid or introduce the capability to carry out load balancing using the cluster's own view and understanding of the state of the cluster, of the servers that are involved in the cluster and the roles that they're playing. And causal clustering involves really two groups of servers. We have a consensus group, the core servers, that support write activity and also are responsible for pushing out replicas of information to the second group, or replicated information to the second group of replica servers that form a periphery or edge around the core. The load balancing behavior, the sort of built-in load balancing behavior within causal clustering ensures that traffic from the population of clients, of applications that are accessing the database, is distributed across those two groups. And we can therefore take advantage of the ability to scale on an increased basis, because the replica servers can have a very large, would typically be capable of, would be possible to have a very large population of replica servers, and the load balancing facility ensures that load is distributed correctly across that pool, as well as write traffic being conducted by the core. And there's another aspect which is related to the idea of causal consistency, which we'll come to in a bit more detail in a moment, which is the ability to maintain an understanding of the state, the relationship between client applications and the cluster and use that information to ensure that users get a consistent view of their relationship to the evolving state of the database. So they carry out writes or updates into the database, they will also be able to see the effects of those writes. And that's an important new feature in causal clustering. So just to sort of recap the aspects that we're supporting with cluster architecture: massive throughput, data redundancy, high availability. All of those things are present in Neo4j as it stands today, but we are moving towards being able to support bigger clusters, particularly in terms of the read workload that can be supported, consensus commit for a higher degree of continuous operation, and built-in load balancing in order to simplify the topology and the work that's involved in actually bringing a cluster into a production environment. So I've mentioned that there's a core and there's a kind of an edge or a periphery. These two groups of servers within the overall cluster play different roles. The core is the consensus group. It gives the fault tolerance to the stream of update transactions, and it ensures that those update transactions will be carried forward for read activity by clients that need to actually see the effects of those transactions. It's typically a small group of Neo4j databases. It would be a similar kind of group, size of group as you might see in an existing Neo4j HA deployment, but it takes responsibility for the surety of the commit traffic as well as the state of the cluster itself. So it's responsible for the safe updating without loss, and including in the event of failures of data stemming from application activity. So writing to the core cluster happens through the Neo4j driver. A application will issue, for example, a cipher command through that driver, or it could be the execution of a procedure that would enable the use of the Java API to request an update. And the update will be propagated to other core servers, and when a consensus is reached, a quorum has actually agreed to, has been able to accept that write request, then at that point, asynchronously, propagation to the other cluster members will continue, but a response will be able to be given back to the driver, to the ultimate client, saying that this transaction has actually been committed, that the write activity has been successfully recorded. So the way in which this is achieved is using the Raft protocol, which I mentioned earlier. Now, the Raft protocol is a relatively recent attempt to rework the area of consensus algorithms or consensus protocols, and in reaction to the perceived difficulty of using Paxos, which was, is a more long-standing existing protocol for achieving consensus. And within Neo4j, we've, as I mentioned, implemented Paxos, and we've also now implemented Raft. And our view is that it is easier to understand. It's proved to simplify our software, and we hope will actually ensure that we're able to provide the right kind of reliability and support more easily for our customers' use of cluster computing. It's also a protocol that's become increasingly widely used by more and more products that require consensus behavior, and that's something that we feel is also useful in terms of providing a broader community and underpinning for ensuring that this is a well understood protocol, and that it is ultimately converges towards a sort of bug-free status. So the way in which the Raft protocol works is to accept update activity through different servers, but then propagate that to the cluster or the protocol group members, and using this quorum approach to ensure that we reliably and including in the event of failure, are able to actually propagate those updates across all of the cluster members. So in the Neo4j context, we have used Raft to implement something that we call a consensus log, which is a log which effectively feeds activity into our existing transaction log within the Neo4j data servers. And that's what leads to transactional updates to the graph. So the consensus log stores both committed and intended transactions. And as those transactions are processed through to the transaction log in the individual data servers, the transaction log is extended in each of those data servers with all of the consensus committed activity, although the rate at which that will occur is not necessarily going to be completely synchronous. One data server may be slightly ahead or slightly behind the other servers, but we have surety that there will be a continuous ordered stream of transactions being processed through each of these servers. So that was talking about the core. Small group of databases responsible for consensus commit and the safety of the data, therefore. If we look at the edge, this is a collection of read replica servers that are designed to provide support for very large-scale query throughput. And this architecture was actually based on the experience of a number of our customers requiring a disproportionately large support for high read throughput relative to the update traffic that was being supported by the cluster. So these servers are not involved in consensus commit. They're not involved in the stability or safety of the cluster as a whole. They are essentially disposable. They can be brought into existence and disposed of in an auto-scaling environment, for example. And each of these replicas contains a fully transactionally consistent view of the state being managed by the cluster. Obviously, there could be some level of delay or lag in terms of replication, which is always the case within a cluster environment. But every single image, each replica within the Neo4j causal cluster is a transactionally consistent view of the graph. So updates are propagated from the core to the edge servers, the replica servers. We've already seen the writes coming through to the core. As those writes hit the core servers, all of the replicas that are registered effectively to receive updates will be on the receiving end of update traffic of propagated replicated traffic, and read activity can be directed to those replicas. It's also possible to read from the core, and that's part of a picture which we'll come to in a moment of, if you like, tunable latency and consistency. So the ability to see relatively more or less consistent views of the data, and there's some trade-off there in terms of the recency or currency of the data that's being viewed. Always consistent, but not necessarily as up to date. So related to that point is the fact that the graph typically is being updated in much smaller units and frequently at a much lower rate than read activity. So we see very often that read transactions cover or traverse a much larger proportion of the graph than write activity. And that's reflected in these two different roles for the core and edge. So looking at that from an application development perspective, I'd like to go in a little bit more detail into how we use the bulk protocol and some evolutions to our drivers to support directing traffic to the right servers for the right kind of workload for those write and read activities. So this diagram illustrates a typical topology where application servers are being used to support ultimate user traffic. That's not really shown in this particular diagram. And the Neo4j driver is instantiated within an application server to act on behalf of the ultimate user and to send requests and to receive responses via the bulk protocol to Neo4j, in this case the Neo4j cluster. We have supported official drivers in Java, Python, .NET, and JavaScript, and there's also a substantial community effort providing support in a number of other languages, and that's something that we at Neo very much committed to supporting and helping those community efforts sort of amplify the language environments from which the Neo4j database can be accessed. For those of you who are familiar with Neo4j 3.0, we have a pre-existing URI scheme called Bolt, and that is used to specify a server which will give access to a Neo4j database. In this context, from a cluster perspective, we want to move beyond access to a single instance, and we want to be able to access the cluster as a whole. For that purpose, we have introduced a new URI scheme, Bolt plus routing. And Bolt plus routing specifies a server in the Neo4j causal cluster which can effectively act as a bootstrap for routing. In other words, that server will be able to give information to the client, to the driver, relating to the topology of the cluster and relating to the endpoints that are available, supported by the different servers within the cluster for different kinds of activity, for example, read activity, write activity, or indeed to support future or further routing requests. But the routing activity includes refreshes based on a time to live in order to make sure that the client is actually seeing and the client population as a whole are observing an up-to-date version of the state of the cluster. So with that single bootstrap address, it's possible to gain access to and then be kept up to date transparently within the driver, that is. It's not something the application's exposed to be kept up to date with the state of the cluster and to have traffic for any particular driver routed in an evenly distributed way across the cluster. So this diagram illustrates the fact that we might have devices or browsers on a PC acting as the agents for ultimate user activity, connecting to a pool of application servers through the drivers to the data cluster, and the way in which the client application indicates the kind of activity it wants to carry out and indicates the driver what kind of server it wants to be routed to is to specify an access mode when sessions are created from a driver instance. So in 3.0 we have those sessions. We have here these access modes which enable a transaction start to the activity in a transaction to be directed to a server capable of supporting write traffic in the core. Read queries similarly are indicated by an access mode of read, and that will ensure that traffic will either go to read replicas or to core servers depending on configuration of the data server. Which brings me to really the last point that I want to go over in detail, which is the approach to consistency. It's non-native graph databases that are based on stores that were not built for the storage of graphs, have a strong tendency to actually exhibit non-atomic behaviors when it comes to updates. And obviously, if you update a graph and you update relationships and you fail to update one end of a relationship, then you have a graph which is effectively corrupt. And that kind of inconsistency is actually very damaging. Eventual consistency is a technique that's used to, after a lapse of time, improve the probability that those kinds of inconsistencies won't occur. And that's a technique that's been used very widely in the NoSQL world. And it's also something in a form that we have in Neo4j, because we don't actually ever propagate inconsistent updates in a cluster, but we can have a situation where lags in the propagation or delays in the propagation of updates can lead to a circumstance where if you read from one server, write in one server, read from another server, it's possible that there may actually be a delay in propagation. So in a kind of global view within a cluster, it is possible to see sort of edge cases of inconsistency. So our single instances are always consistent. Any particular replica you look at is always consistent and exhibits, the fact that we've got atomic transactional updates on the graph, so we never have corruption or inconsistency in that sense. But that isn't quite where we want to be. And in 3.1, we've tried to address this situation and move to a different state relating to this concept of causal consistency. So our causal consistency, the problem we're trying to address is something I've already referred to, which is that cluster members could be slightly ahead or behind of each other in terms of the update traffic that's traveling through the cluster. What we want to do is be able to give users a view which is consistent during the course of their experience and usage of the database over time. So the property we want to really ensure, or properties we want to ensure, are sometimes known as read after write, or read your own writes, and read after read. That's to say, if a client application has written data into the database, it should always see that data in any subsequent access of the database. And if it's read data, it should never go backwards in time, as it were, when it rereads that data. So if we can guarantee that's true over the passage of time for any given user, we can effectively eliminate those edge conditions that can come out of eventual consistency. And in order to do that, we may actually have to cause slight delays in terms of access to make sure the replica we're using is up to date from the perspective of that user. That's usually not true, but it may occasionally occur. And so this is a tunable behavior. It's not something you have to have. You can choose the pre-existing eventual consistent behavior, but there may be some latency cost. So I'm just going to walk through a sort of semi-realistic use case here that will illustrate this. And I think that many people that we've talked to are familiar with this kind of problem. You've been browsing a product catalog. You want to actually make a purchase. You need to create an account in order to do that. And once you've created that account, you need to carry out a login. When you create the login, you can very frequently find that you're not yet able to do that the account hasn't actually been made available for the purposes of actually carrying out the login or going ahead in order to register an order against the account. And that's actually experiencing eventual consistency, which is to say, to begin with, it feels inconsistent. I created my account, but it's not available to me. So a few moments later, typically you can actually go ahead with that login, and that's the kind of problem that we want to eliminate. So that was an experience of eventual consistency. Illustrating it by showing some activity being carried out on the database and the results coming back. Without the causal consistency behavior, we can easily see that we haven't yet got the data that's shown in red, the transaction 11 yet updated to a particular replica, and therefore it appears this account has not been created. So we address that with this notion of causal consistency, which is something that was originally looked at the time when eventual consistency was defined in research work in the mid-90s at Xerox PARC, but has actually been implemented, as far as we know, apart from in Neo4j 3.1, only in the Azure document DB database. That may not be the case. There may be other databases that have got to that point as well, but we've certainly seen this as being a sort of leading edge feature. And we use a technique called a bookmark to enable causal consistency to be effective, and that comes down to providing a session token, which is opaque to the application and represents the ultimate user's most recent view of the graph. That token may actually be evolved to support additional behaviors in the future, but that's currently what it represents is an understanding of the position in the transaction stream for a particular user. And if I show the sequence that we were looking at previously using bookmarks, the update activity is matched by, on the response from the update transaction, a bookmark being passed back which can be made available to the device or browser, and then used as a context to effectively reposition on that bookmark and to establish the state of the user's interaction with the database, even though the application server that's being used in this example is a completely different one. It had no involvement in the update transaction. And that leads to a pause in terms of the starting of the transaction until the replica that's concerned has actually received the update concerned, so that we get a completely consistent view provided. And that will mean that we will not experience this sort of glitch of an account that appears to not exist. To do that, we enable bookmarks to be extracted from sessions, and we then allow those bookmarks to be provided when transactions are begun in another session. And that allows the logical chain of consistency to be maintained between the different applications that are supporting activity on behalf of the same ultimate user. And we can see that the bookmark which has been obtained is used during the course of, in this case, of read activity. And that can be carried out both for read and write activity any number of times to superimpose a causal consistency chain across the activity on the database for that particular user. So that really brings me to the end of the description of what we're doing with causal clustering. A core for updating the graph and maintaining continuous operation in a consistent way, and an edge allowing queries, analysis, and reporting via read replicas rather at large scale. So be very happy to take questions at this point, or to see questions coming up relating to this in the course of the fireside chat as we move towards the end as well.
Great, thanks a lot, Alistair. We have lots of great questions coming in from the audience here, so let's take some time to take just a few of those. So the first question for you is, how does this new clustering architecture impact the size of a typical deployment? Say with Neo4j HA, I have one master and two slaves. What would be sort of an equivalent size of the deployment with causal clustering?
Well, I think we're going to see fairly similar sizes in terms of having the appropriate number of members of a consensus group in the core able to support continuous operation. So a cluster of 3 or a cluster of 5 would be a typical size for the consensus group. If read replicas are brought into the picture in order to distribute the read load, then those servers will be additional to that core group. The sort of sizing of the consensus group is similar, because the behavior of maintaining the membership of the cluster is something that happens in HA and in causal clustering, but we also use that consensus group to ensure that we've got consensus on commit activity. Doesn't really affect the typical number of servers that will be required for a consensus to be formed, but there's a double job being done by that same group of servers.
Okay, great. And we have a lot of questions sort of looking at clarifying the consistency model. So I'll sort of synthesize a few here. So one, is it correct to say that Neo4j is moving from an ACID database to a base database? And then also, is it correct to say that in CAP terms, consistency, availability, and partition tolerance, that Neo4j is focused on the AP piece of that?
Well, I'd say that we're not moving away from ACID. What we're actually doing is we're trying to get a stronger level of consistency, given that we are using a replication approach for high availability, which makes it very difficult to give full, strict transactional consistency at all points for all accesses across the cluster. Although that is a direction which, from a number of angles, I think that we will be, pursuing as the product evolves. So the ACID quality of transactional updates on Neo is not being altered. Every update takes place within a transaction. The issue is as those transactionally consistent updates are propagated, are replicated, can we do better than we've been doing previously in terms of providing a consistent view of the data? And I guess, sort of relating to the second point, one of the things that causal consistency lets you do is effectively maximize the consistency that you can achieve whilst having high availability. And this technique of causal consistency really takes us one sort of step up in terms of a sort of ladder of consistency capabilities. So when it's not an evolution away from ACID. It's trying to bring a view for a given user that is as close as possible to a fully ACID experience.
Okay, great. And just one more question before we move on here. And the question is, with this new causal clustering model, are we able to deploy across multiple data centers?
Yes, that can certainly be done. We have we've seen a number of cases where people are thinking about doing exactly this. That they're thinking in particular of having a consensus group, a core, which may be located in one data center, but read replica or pools of read replicas in other data centers. That's a model that's already come up from 2 or 3 customer cases that I've seen. So certainly the cluster is capable of operating across a wide area network as much as it is within intra data center. Obviously there are implications in terms of network distance, which would have to be taken into account in terms of the currency of replication and the behaviors the effects that might have in terms of behaviors that are supported by an application. But it can certainly be done in principle, and we're actually intending in sort of future versions to sort of strengthen those multi-data center capabilities and exploit a more tiered architecture for the read replicas to actually make it easier and more efficient to distribute updates across a multi-data center topology. So this is certainly something that's that's intended as part of this architecture and the way in which the architecture will evolve.
Okay, great. Really good to know. So thank you very much. Let's go ahead and move on to our next session here. So coming up, we have Igor, who will be going into a deep dive on some of the new security features in Neo4j 3.1. And just a reminder, we will be taking a few questions at the end of Igor's session, so please feel free to share those as well. And with that, over to Igor.
Thank you, Will. So security and causal clustering are, in my view, the centerpieces of 3.1 release. In this 3.1, we completely revamped the security architecture to satisfy the needs particularly in a couple of industries, but particularly in healthcare and in finance. And we took a huge effort to do that. We've been working on this for more than a year. And you may wonder, why did we took such a big effort? And as Emil mentioned earlier on, where Neo4j was previously used for graph-specific use cases, what we see now is a shift to enterprise standard, to Neo4j being used as enterprise standard. And what it means in most practical sense is that while previously you had a Neo4j deployed in a single department, being used to provide the recommendation insights and being consumed by a single application, now you have Neo4j deployed across different departments, being used by multiple different people who have different access rights, different needs to see connected data, and they're all making so much use of this connected data across the departments. So they're really unlocking the value of the data in their enterprise. But that brings with itself the need to safeguard the data and meeting compliance requirements. So in this release, a couple of really exciting features. Previously, we had only one user, Neo4j. Now we are enabling multiple users with Neo4j. And we have a very flexible authentication, options. I will talk more about that. We're introducing role-based authorization with a fine-grained access control through what we call a procedure-based views. We have introducing ability to list and terminate running queries. And we are also introducing ability to log all of the security-related actions, and we're going to talk more about that. And as I mentioned, this enables us to set on a path to, in the future, if we want to certify Neo as compliant with a HIPAA, PCI, things like that. So on authentication options, so Neo4j here has a couple of different options that you can use. You can use a built-in native user repository, and we recommend that to be used in a testing, POC, single instance deployments. We built a couple of powerful UI widgets to explore how you can create multiple users, you can add roles, things like that. Once you move into production, what we've seen from our customers that they already have identity and access management systems deployed, and typically these are Active Directory or Open LDAP systems, and we built a connector so you can connect to those systems, so you don't have to import and redo all the user creation, all the role creation, and all of that. So we can just plug in your existing enterprise architecture, and I'll go through more details on that. If you're not using typical identity access management, if you have a specific need in your environment where roles or access rights are even more dynamic, and there maybe need to be programmatically specified, what we did here, we introduced what we call authentication plugin extension module, which is a set of exposed APIs. So you can build your own Java in Java language or any other in Java compatible language. You can build your own authentication custom plugin and deploy it, and that plugin will then serve all the authentication and authorization needs in your environment. It's extremely powerful. With that, you have basically a Swiss Army knife to deploy any kind of security scenario you want to. So more details on LDAP. Let me see. So this is neo4j.conf, a typical configuration file that we store all our settings. It's a single line enablement of dbms.security out provider equals LDAP. This is how you turn on our LDAP connector. You need to specify the endpoint for your LDAP service. This can be a single LDAP system or a cluster. You can even specify a custom port number. You can specify LDAP S. You can specify a system account to use to access LDAP. So for all the authorization and authentication pings, so most of our authorization, you don't want to use the username and password to go through the network. You can use the single system account to check that. This is a kind of a best practice, and you specify directory structure of your custom LDAP. So every customer's LDAP configuration is different, and it's very custom, it's very specific. So with this, we have a very rich ability to adapt to any kind of directory structure you have in your environment. So let's look at an example of that. Let's say you have a base DN of example.com, and you have created a directory called people. You also have a directory called groups. And for people, you created a couple, let's say Bob Smith and Carl Jr. And for the groups, you created Neo4j read only, Neo4j read write, and of course you mapped let's say Bob Smith to one of these groups, and you mapped Carl Jr. to one of these groups. And this still doesn't tell you how does it work with Neo. So that's a good question. So you need then to map these Neo4j permissions, again in neo4j.config file. So we map this Neo4j read-only group that you specified in your LDAP. We map it to this system keyword called reader. You can map it to the system keyword publisher and architect, things like that. So the question then is what is this system keyword reader and publisher and architect? So here we have defined 4 predefined system roles, and they are reader, publisher, architect, and admin. Reader has an ability to read entire graph. It does not have ability to write and update data, to do any schema operations. It can terminate its own query, of course. Publisher has abilities like a reader, but on top of that, it can update and delete data. Architect can do everything as publisher, but they can also manage index and constraints. So it's more like a schema operations, and as we introduce more schema types in the future, the architect role will be fully fleshed out there. And admin can do all of this mentioned before. In addition to that, it can manage the built-in users, like creating users, creating roles, deleting users, deleting roles. And it can also terminate other people queries. So you can find the long-running query and it can terminate that. It can suspend the users, things like that. So I mentioned earlier, so this is a role-based authorization that we're now introducing here. Now we have multiple users, we have a role-based authorization, but all of these roles are graph-wide. And I often get a question, but specifically, sometimes I have a situation where I have a graph where parts of the graph has a secret data, is a PII data, and how do we do that? And this works better when the graph is when the slide is being built, but just for this purpose here, let's say we have a graph that has a company name and address, and then company has employees. In this case, we have employee name, address, and social security number, which of course is secret data. Same as here, and then every employee has employee data and salary on that, which is also restricted access node. So we can build a procedure, let's say get employee details for a company, Acme, and that procedure is almost like building a view. That procedure would only access the nodes of the company. That's where we search for a company name equals Acme, and it will also return all the nodes of its employees, but not the field SSN here, and then same as here. And you can also have a procedure that updates these details, but it also does not access SSN, and we can give access to execute this procedure to the Carl Jr., whilst some other people in your environment, let's say Bob Smith from accounting, he needs an access to employee salary details. So he has a different view defined here, and he has access to all the properties in employee node and as well as salary. So what we do here, we just do not give Carl Jr. or Bob Smith reader access or writer access to entire graph. We just give them access to execute these procedures or views that we built for them. And as we move on in the next release and then further on, we will be expanding this model of views and dynamically allowing people to access sub portions of the graph. And I think one interesting thing is that about security is that unlike the problems we have with GoToMeeting, technical glitches, which is understandable, in security you can't have technical glitches. You can't have things that may work, may not. So in this 1 year that we've been working on security, we focus on 2 things. It's thoroughness and simplicity of use. It's very important to make it easy for users to use security in Neo, so you don't make mistakes accidentally. And it's very important when once we implement this that it works really well. So in that sense, we built this really nice UI widgets. This is for the native users. If you're in a Neo4j browser, you just type server user add. You have this nice UI where you can just enter the new username. You can select from the drop-down menu which role you want to assign to this user. You can set up an initial password and even require on the first login, a password change. You can just click here and the user is being created. Similar widget here is a server user list, where you just have a list of all users. You can then suspend or activate users. You can delete users, and that's all being logged. And I'll talk more about that. Another feature that Philip talked earlier is ability to list and kill queries. Again, we built a nice user interface to do that. Here you can see now we have multiple users. You have 3 different users running queries on this system: Neo, Neo4j, and Tank. We can see the string of the query being executed, and we see which parameters are passed to the query. And really interesting feature here is that we are now allowing to specify metadata with your query, so you can pass any number of key value fields, such as, like, for example, originating user, things like that, so it can really enable you later on when you're going through the logs to understand who's running what. If you have, for example, one application accessing Neo and then there's multiple users are accessing your application, here you can see an elapsed time, and you can kill long-running queries here. This is UI if you're using Neo4j browser. Of course, if you're using a new command line tool, like Philip mentioned earlier, a Cypher shell, you can execute predefined procedures to list queries, to add users, things like that. So all of this functionality is available also from the command line. You don't have to use these UI widgets. But we believe that this simplicity is really gonna bring these features to life. We are also introducing new security log. Here you can just see a couple of actions I did to demonstrate this. We have a Neo4j user logged in, has created a user Tank. I added a role architect to the user Tank, and you can see later on the Tank logged in, and then Tank tried to do something which was not in his permission level. Because he was an architect, he cannot list users, he cannot add users. So we log here all the actions that were successfully completed, but we also log actions that are not allowed in our security model. So we believe this is also kind of a good feature for you to kind of keep track of what's going on in your system. We did quite thorough testing of our security features. We did a penetration testing with a third party, and we were quite confident, very confident that we have thoroughly implemented these features. With that, I will open to the questions.
Okay, great. Thanks a lot, Igor. We're getting some great questions from the audience here. So one question is, what use cases or industries do you think are a good fit for this? Are there certain use cases that stand to benefit the most from these new security features?
Right. So, I mean, obviously we get a lot of traction from healthcare and finance industries, just specifically because in healthcare, for example, there's a lot of connected data, so people from different departments can use and harness the value of the data. And it's interesting industry because it's also specifically has a lot of privacy concerns. So I think healthcare, finance are example industries that this is going to be very welcomed. But more than that, I believe as we are seeing this trend from us being use Neo4j for graph specific use cases and more to the kind of enterprise standard, I believe across all industries where larger enterprises are using us across departments in multiple different use cases, security is just kind of sine qua non. You have to have security to deploy Neo going forward.
Sure, absolutely, that's great. And we're getting lots of questions asking about upcoming security features, specifically asking about encryption, both at rest and in transit. Are these in the pipeline?
Right. So there's definitely encryption and transit. We have a Bolt, a new binary protocol now, and with Bolt we support TLS, SSL encryption, and we have a configuration options to say require SSL so you can't even connect to your server from your client if you're not using SSL. Same with our connector to LDAP. You can say start TLS required, so you have to use SSL. So as far as the encryption in transit is concerned, I think we have covered that field. We will do more work around mutual authentication in Vault, but with the ability for the clients, and what we recommend as a best practice, with the ability to supply your own keys for encryption in Vault, I think this is as solid as it is. As far as the encryption at rest is concerned, we do recommend our customers to use volume encryption at the moment. And if it's even more, if the needs is such that there's even more stringent requirement, we do recommend them to use application level encryption. So then it's end-to-end encrypted, like PI data will be then end-to-end encrypted from their application all the way through the disk and back, and even in memory. That being said, we are considering to explore ourselves to provide some kind of a volume encryption. We are also exploring and even started doing some POCs and working on introducing a support for Kerberos in addition to LDAP.
Oh, okay, great. And let's just take one more security-related question before we move on here. So here's a question from the audience. Does the Active Directory and LDAP authentication extend to the Neo4j browser?
Yes. So what happens is that browser is just a client to Neo. So when you are logging into a browser, you are effectively browser is just passing the credentials to Neo, and then you're authenticating against Neo with those credentials, and Neo is then using LDAP as a backend to say if this principal is allowed to log into Neo or not. What the question maybe was more about, do you need to specify a fully distinguished name in the browser or not? So for that, earlier I showed some LDAP settings. There you can actually specify a way how to, for Neo4j, to translate the short username that you then specify in the browser to the fully distinguished name, and that's the fully distinguished name is then used to authenticate against LDAP. So, but yes, of course, browser is using LDAP at the end.
Okay, great. Thank you very much.
Perfect.
So let's go ahead and move on to our next session in the agenda here. So next up, back to Alistair Green, who's going to give us an update on the OpenCipher project.
So I want to talk quickly about the OpenCipher project. This is a project that we announced in the last quarter of 2015. The idea was to take the Cypher language, which has been in Neo4j since 2011, and has proved to be an extremely popular way of making it easy to access data and update data, graph data within the database, make that language much more widely available, and to effectively try and push towards arriving at a situation where Cypher becomes the SQL of graph databases. Obviously, having a language like SQL operates in a sort of declarative level, in that kind of ecological niche, which is independent of general purpose programming languages, has proved to be an extremely powerful tool and accelerant for, first of all, relational database adoption, and then for the development of tooling around the relational database world. And we'd like to see that happen. We think that a lot of other vendors actually share the goal of having a standardized language in that kind of space. So we're working through a process of helping people implement using Cypher, helping to provide artifacts which will more precisely define the nature of Cypher as a de facto standard language, and with the goal of moving over time towards a formal open standards process adoption of Cypher as Cypher evolves and begins to be more widely used beyond Neo's products itself. So in 2016, we've created some artifacts which are Apache or Creative Commons licensed, EBNF and ANTLR grammars, railroad diagrams, and syntax documentation, and we've taken a very large number of scenarios, tests out of the Neo4j product and translated them into Cucumber-based scenarios which enable language-independent confirmation or checking of compatibility with the definition of the Cypher language for other implementers beyond Neo. And that's allied to a Cypher improvement proposal process where everything's centered on GitHub. We've got public documentation, and people are very much encouraged and free to contribute to the process of thinking about ways in which the language could evolve. So some of the things that have been discussed, and we're discussing more and more extensively at the moment, are potential for increased schema capability, increased typing capability, name graphs and views, the whole issue of multi-graphs, more powerful path expressions. So Cypher is very much a language which we intend to evolve, and which we see there being a number of areas where we could take it forward and improve. There are several active projects. Just to pick out a couple here, there's very interesting IDE support for IntelliJ IDEA from Neo4j. That's an interesting plugin that's getting a lot of downloads. There's some research projects that have looked at using Cypher, and there are some other sort of tooling projects relating to language-specific parsers. In terms of commercial data engines implementing Cypher, we started off with Neo itself in 2011. SAP have just announced support for use of Cypher on the read-only side in HANA Graph, just this right at the end of November, beginning of December. As they point out, they're leveraging the fact that Cypher query language is de facto open industry standard for graph processing. It's certainly used much more extensively than any other language that we're aware of in that kind of position. And there's a company called Bit9 who are just about to introduce a beta release of a product they intend to go GA with in 2017 called Argens Graph. So we're seeing both tooling and database implementation beginning to push forward. And in the research field, we're seeing some interesting things like the use of Cypher in streaming queries. So in 2017, we are beginning work on a semantic specification, and we're both looking at work on natural language and formal mathematical specification of Cypher. We're also going beyond the existing effective reference implementation of Neo4j itself and starting a second implementation, which is very much focused on cluster analytical processing workloads, which will also be used to illustrate advanced and experimental features in Cypher. And we're having the first Cypher implementers meeting immediately before the Linked Database Benchmark Council meeting, which is taking place in Waldorf in Germany in February next year. So a lot going on. I think there's going to be a lot more going on. We've got a big emphasis within Neo on not just open Cypher, but also evolution and performance improvements with Cypher within the Neo4j product in 2017. So I think there's going to be a lot more to say in future meetings like this. So questions, I think, are probably going to be held off on this one for until the fireside chat.
Great, thanks a lot, Alistair. Really, really exciting project. Great to see that progressing. So next up, we're going to be hearing from Jim Weber, who is our chief scientist. And after Jim's presentation, we will have a fireside chat question and answer panel. So please keep asking us your questions, and again, we'll bring everyone back for that. So for the fireside chat, we'll have questions opened up to the whole group. And so with that, over to Jim.
Hello. Just checking that you can see my screen. Will, is that all looking okay to you?
Looks great.
Fantastic. So I realize that we are somewhat up against it in terms of time. So I'm going to go through this relatively quickly. And apologies, Will, that I seem to have jumped in and taken your session. I hope this will be well. And for those of you online, I've been furiously deleting slides as we've been going along, just so we can fit this in and still get the fireside chat in. So I've got the best job amongst all of these people, including the two lovely guys who sit next to me, because I get to sit and play with Neo4j technology and see where we can take it in the future. And I think what's wonderful about 3.1 is that it sets such an amazing platform for useful stuff right now. you can take Neo4j 3.1 right now and do some amazing things with it. But from my point of view, it gives me an amazing platform for evolving the technology, and for all of the my fellow research and development team here at Neo4j, it provides an absolutely amazing platform for us to do some astounding things in the future. And not all of this is coming from the software space. I don't know, I guess many of us are software folks on this webinar, but the hardware folks have been busy. And it's been really interesting to me because for the longest time, I've got these guys kind of almost written off as boring beige box vendors. And a computer is a computer is a computer. But it turns out some rather amazing things have happened recently, particularly around the way that memory hierarchies are arranged in computers. So it turns out that up until a few generations of Intel ago, the source of truth was RAM. In fact, my PhD is in parallel computing. I have this terrible habit for thinking that values in computer memory are only visible when they're right the way out there in main memory. And that's not true anymore. Something really interesting happened, that Intel decided that the source of truth for values will be L2 cache. Okay, well, why is this? Why am I talking about RAM and cache and all this kind of stuff? It has profound implications for the way we write software. If I'm going to, if I accept that the source of truth is L2 cache, which it is, and therefore L2 cache is where all the action is, I need to optimize my software for L2 cache. And we've seen Neo4j. Philip mentioned the high limit in his presentation a little while ago. And that high limit format did some amazing things in terms of what you can store in Neo4j. You can now store like something ridiculous like 400 quadrillion objects or something insane like an infeasible number. But what it also did as a side effect of doing that, it gave us relative pointers. Effectively, it gave us pointer compression, which means now we can fit more of the graph into that L2 cache, which is where all the action happens, which is where all the fast stuff happens in cache, all fast stuff happens in a computer. Which means that you may not have noticed, but as you simply upgraded to that version of Neo and adopted the high store limit, things just got quicker because we were using the best part of the computer to do those graph traversals. I'm going to come back to that in a moment. I think RAM is something that's super interesting. There is a professor from Stanford called Yuri Leskovich, and he's been observing the size of dataset growth versus the size of RAM. And what he's observed is something which I found kind of anecdotally difficult to believe, because we all know, or purport to know, the data set sizes are like 4 million times bigger than they were last year, and every year we produce more data than we have atoms in the universe in all previous years, and all those kind of like slightly shonky statistics. But actually, when Jury has done the work, actual quantified work, he observes that while data sets are growing larger, they're growing larger at the rate of about 20% a year, whereas RAM is growing at the rate of 50% a year. Remember, boring beige box builders? They're not so boring now. And if you look at what Pafka has done at datascience.la, he's done a bunch of work on typical data set size. And actually, what we observe is that between kind of like, megabytes to reasonably small numbers of gigabytes, up to around 10 bytes, is the vast number of data set sizes fall conveniently into that size. Sure, there are some outliers of petabytes of data and so on, but for the most data that we work with, it fits into kind of gigabytes to terabyte scale. And what Jure also points out is that actually buying with terabytes or renting machines with terabytes of RAM isn't science fiction anymore. It's within the kind of cost that we could afford as software developers. It's not space shuttle cost, it's cost of a developer cost. And so it makes a very interesting point that if you want to do big graph analytics and take advantage of all that locality that we have in the graph structure, simply get a big machine. Another interesting point, right? RAM or storage is converging. We are starting to see the convergence of secondary and primary storage in the form of non-volatile RAM. What would this mean for something like Neo4j as a database? Well, it means that instead of dealing with optimized formats for RAM and disk in between them, we could have a single format designed for storage on the non-volatile RAM. Sure, it's slower than normal RAM, but it's non-volatile and it's huge, and that means that we can have this kind of really interesting trade-off between the volatility of our main memory the size of it and the speed of access to it. It's still, of course, faster than secondary RAM. So you've got all these interesting forces happening in the hardware world, a world until a few years ago I'd kind of written off being the next generation always comes and so on. But things got super interesting. I think nothing more so than the fact we're starting to see coprocessors. We're quite used to the idea of coprocessors for things like graphics. We're quite used to the idea of a GPU being a specialized processor for graphics. But we're now starting to see things like IBM's Power 8, which is effectively a specialized coprocessor for I/O. And so some of the IBM experiments have shown extraordinary speed-ups when offloading the I/O work onto this specialized processor. Now, I'm not a hardware person, but why am I interested in this? Because it fundamentally changes what we can do on modern hardware. For example, my CTO, Johan Svensson, wrote up some workloads that would test Neo4j on modern hardware and really try to push the envelope. And we had a commodity processor, commodity dual Xeon processor, and we decided that we'd build a social recommendation. So something like, tell me about something that my friend bought because I would want to buy it. It's a kind of, a very awful reflection on how fragile human psychology is, that we all want our friends' stuff. When Johan ran this experiment on this commodity server, he found that, as we increased the number of concurrent threads doing the work, we could, on this commodity dual processor server, get somewhere between 36 to 60 million traversals per second. So you can explore really quite a large large graph in a relatively short space of time on commodity hardware, because this commodity hardware is actually quite powerful. What does this mean in terms of us as application builders? It means that we can put this stuff online. We can put it in between a web request and web response and get really useful stuff done in those tens or hundreds of milliseconds that we're allowed before the user browsers elsewhere, and really get them hooked on our proposition. So Johan, while he was doing this, also decided that he would just simply try and burst the limits. And he actually built a system where we stored 1 trillion relationships on a single server on a large disk. And then we sustained 100,000 user actions a second, so reasonable user activities per second. And this is interesting, right? Because even on a machine where the RAM, the part where we tend to cache graph, was far smaller than the overall disk size, 33 terabytes in this case, we were still able to do 100,000 user transactions a second, which is kind of interesting, and trillions, as Professor Brian Cox says, is not an actual celebrity endorsement. On the right side, Johan and his team also imported the Friendster data set. It's about 1.8 billion relationships. It takes about 20 minutes. That's 1 million writes per second. It's pretty quick, right? So this modern hardware, Neo4j is able to take advantage of that as a native graph database and really, really pile our data into the database, funnel database in there exceptionally quickly. Thanks, Brian. Still not an actual celebrity endorsement. So let me break this out for you. This is 1 million writes a second on trillions of records and 50 million traversals a second. You can achieve an awful lot with that power at your disposal. How is Neo able to do this? Neo's able to do this because it's a native graph database. It means that each level of the stack, from the query language, which Alistair spoke about, right the way down through the clustering, right the way down through the RAM and the disks and the memory hierarchy, at each point in that, we can optimize for graph workloads. This isn't some grafted on API on top of a relational database or some other database. This is designed specifically for graphs all the way down the stack. If you don't do that, if you choose to take a graph-like API, and if you'll excuse the pun, graft it onto, that was an awful pun, I'm sorry, I apologize, I retract. If you choose to graft it onto, there we go, yeah. If you choose to graft it onto a non-native database, none of these optimization points are available to you. And I saw something like this. So there were some guys on the internet. It always starts with some guys who were wrong on the internet, right? And they had publicized some ongoing experiences they were having in a graph library on top of some eventually consistent NoSQL store. And they decided they were going to do what they thought of as big graph, 10 million nodes, 100 million relationships, so kind of a scale-free graph. And this is the setup they had. They had a rather large cluster, 6 machines, each with 48 CPUs, 256 gigs of disk, 256 gigs of RAM. And they did a bunch of graph operations on it, counting nodes, counting rows, kind of looking for patterns, typical things that you might want to execute in Neo4j. And I saw this, I thought, wow, that graph is it's fairly modest in size compared to what Neo4j can hold. So I thought, well, let's I'll run these in Neo4j. So actually, we imported the Friendster data set, as I said again, and it's slightly bigger than the graph that the other guys used. But because we're native, we just scored brilliantly at this. So count nodes, 201 seconds on the non-native GraphTech, less than a millisecond on Neo4j. Now, I only know it's less than a millisecond because I set my timer to be millisecond scale and it said 0. So all I can tell you on count nodes is that we are at least 200,000 times faster than non-native tech. Count outgoing wells, I can tell you that we are at least 200,000 times faster on one thread on my laptop than this big, beefy, macho-looking cluster. And so it goes on, counting outgoing wells at depth 2, order of magnitude faster. Outgoing wells at depth 3, still 100 seconds or faster or so. I happen to know that particular database optimizes for depth 3, so I think they score well there. Group nodes by property value, a fraction of the time, kind of 8 seconds versus 212, so 4% of the time, cost time. 4 times faster for grouping relationships by types. Twice as fast for kind of knows and likes relationships. And even on something on something as Graph Global as PageRank, we are a fraction of the time, 27 seconds versus 2,500 seconds. Now the asterisks, I should tell you, those are the ones I didn't run on my laptop. My lovely colleague Michael Hunger, who I'm sure practically every one of you know, lent me a beefier server because my laptop only has 16 gigabytes of RAM and Michael's had a few more. And so I ran them on a single server at Michael's house, which was good of him. But even so, across the board, because we're native all the way down, we're able to optimize for graph operations. And what does this result in? This results in just extraordinary performance power for you when you're doing your graph analyses. So my colleague Alistair discussed causal clustering at some length, and I think you guys kind of know where we're going with that. Causal clustering provides large scale, but with a strong consistency guarantee that you will always see your own rights. You will never be left wondering, did my right propagate yet? So that's an achievement unlocked, as far as I'm concerned. We've got causality at large scale. But we're not stopping there, right? My job isn't to just kind of declare victory at the first kind of interesting state. Today we have causal clustering, in fact, literally today, but we're going to do more things there. So at the moment, as Alistair mentioned, we have a load balancing scheme that's baked into our end-to-end drivers plus causal clustering system. But actually, we can adjust that load balancing mechanism. We can make it topology aware. So we will start to be able to do more sophisticated load balancing around the cluster based on server load or geography or affinity or user preference or anything else that we might want to do. Ditto, today all of the read replicas appears. They're all replicated from the same core set. But in the next version, we may be able to offer a whole range of capabilities in terms of catching up from nearby read replicas or catching up from replicas that are substantially underloaded or just a user preference or a geo preference or any of that kind of stuff, which will give you a really nice idiom affordances for being able to do multi-data center clusters. So that's great, because that will be causality at very large scale achievements unlocked. But again, we're not stopping there, right? What we really want to do is take this profoundly solid platform, which is causal clustering, and be able to grow it to something even better. Now, of course, the reason that we love Neo4j so much is its traversal power, right? I mean, aside from its brilliantly helpful acid semantics and the causal consistency semantics, really what we like about Neo4j is that I can hop around my graph in a myriad of different ways to find answers quickly. And we've always had the ability in Neo4j to follow a relationship from tail to head or head to tail at exactly the same cost, because all we're really doing is pointer chasing. And that's interesting because in order to maintain that semantics, even as we would potentially try to break the data up to partition the graph amongst collaborating computers, we need to maintain that two-way semantics. This leads to an interesting design trade-off in distributed computing between availability and reliability, where availability is the ability of a system, try to avoid using the word ability, to provide an answer. Not necessarily the right answer or the latest answer, but an answer. Versus reliability, which is the capability of a system to provide the correct answer. And actually, according to FLP, so some folks asked about CAP earlier, FLP is the deeper magic that came before CAP. According to FLP, we know that we cannot have both. So there's an interesting design trade-off there. And you can see that here. This would be, imagine a database expressing the undying love of the United Kingdom for the United States. You can see there that very clearly that the UK loves the United States. We don't know about the other way around, we hope. We don't want to be in the bad books. But right now you can see that the two records on each part of a partition are sympathetic to one another. They're mutually consistent. But if then we had updates going on, concurrent updates going on, we actually don't know how that would be. Is it the case that the UK loves the US or not? On the left-hand record, we can see that the UK, someone on the UK's behalf has increased the value of the love, and someone on, in this case, France's behalf has removed the love. And the question arises, well, which one of those is true if they happen concurrently? And in those systems that have weak consistency models, the answer is, I don't know. And frankly, that's not a good enough answer. And we need to have some determinism about this. We can't just leave this to sloppy, eventually, which means maybe, consistent, last right wins kind of nonsense. We need to understand whether a relationship exists or not, because we're going to make decisions, business decisions based on that. You know, in this case, if we don't love the US, maybe our trading relationship dissolves with them. And goodness knows at this point in time, we need all the trading partners we can get. So in this design trade-off, Neo4j chooses reliability. The question earlier about are we AP, CP, blah, blah, blah from CAP, actually we're CP. When push comes to shove under pathological conditions, I fundamentally believe that we should not give the wrong answer. And that makes us reliable. It doesn't necessarily make us unavailable or poorly available, but it means in CAP terms, we favor reliability over availability because we need to stay correct. And the moment we don't stay correct in a graph, the corruption, the logical corruption will propagate through the graph. As we know, pathogens propagate through a human network. So we choose reliability. You're going to see some interesting advances in that stuff in coming years. The team in the R&D labs at Neo are going to be putting out some pretty advanced stuff. But we're also working on the query level, query language level. Alistair talked to you about OpenCipher and the progress in opening up Cypher to the rest of the world, but we're also working on our own Cypher implementation internally. For example, you can see here a typical Cypher query. And as a human, you can kind of look at this and you can already see opportunities where things could be executed concurrently. These different matches, the merges and so on. You could, for example, run the two different matches in parallel and then pipeline the results from those matches into the merge clause. So you've got two opportunities at least for parallelism there. And as a human, it's kind of easy for me to spot this. Cypher at the moment can't really easily spot these, but Cypher actually is just when you boil it down, it's a tree of operators. And so we could actually, as we do today, cost those operators, but we could even cost them with respect to available cores or available capacity on a machine. What does this mean? It means that we now have an R&D project underway where we will be looking at parallel Cypher. It means that you will be able to apply all of the compute resources in your box to solving a particular Cypher query. So it's going to be great for analytics. Or you could look towards sliding the dial over a little bit for that particularly extensive query that you run in RTP mode and allocating more of your computational power to it so that it runs quickly so you can get it done in that real time that users demand. So this is absolutely great. This is fascinating stuff. It actually harks back to my academic heritage. This is going to make a profound difference for those of you guys that want to run large graph queries in Neo. It's going to make a profound difference to those of you that want to run fast RTP queries that consume multi-cores on Neo. So keep your eyes out. That's going to be coming over the next months and years. It's going to make it into Neo4j just as part of all general Neo4j code. So that's it from me. I have one thing to say, which is the best thing, which is download Neo4j 3.1 GA right now. It's available at neo4j.com/download. Please have a go with it, build stuff with it, tell us what you love about it, tell us what you hate about it. Enjoy, and thank you for listening.
Great, thanks a lot, Jim. That's really exciting stuff to hear about. So for now, we're going to spend the next maybe 10 minutes or so, going through a fireside chat. We'll have everyone from the panel available to answer questions. I know we're over time, but it's not every day that we have this great team together, so I'd like to take advantage of that. For those of you keeping score, we did drop the using Cypher procedures and functions session in the interest of time. But we'll go ahead and do that as a separate webinar later on, so we can spend some more time talking about that, because those are some exciting features as well. So look for that as a separate webinar coming up soon. And so with that, let's go ahead and get into some questions here. So I think this first question is most appropriate for Emil. So Neo's recently raised a $36 million Series D round. How do you think this impacts the world of graphs? And what type of investments is Neo4j going to make internally with this money?
Perfect. So Will, can you hear me? Can everyone hear me?
Yes, absolutely.
Perfect. Yeah, I guess it's kind of telling when I said 2016 has been a great year and these are the things that have happened, etc. I kind of left out that minor little thing, the fact that we raised a fairly substantial round of investment. We're super excited about that. I think that there's a number of things that we want to do with it. But the primary use that this will lead to is an investment, in particular, in engineering, so in product. I think that Neo4j is an amazing product, but we're very ambitious and we have very high goals. And there's a lot of things that we want to do. I mean, Jim just spent 20 minutes talking about some of the things, some very exciting things. I think that session could easily have been another 20 minutes or another hour or 2 hours, because there's a lot of stuff that we want to do and we want to build into the product. So that's really what I'm most excited about, that this round of financing will enable us to do, deeply invest into the product.
That's great. Really looking forward to that. So the next question we have, Philip told us about some of the awesome new features that Neo's been able to build out this year and in 2016. Can you tell us a bit about what's in store for us next year in terms of product, Philip?
Sure. So Jim mentioned a few. The very first thing you're going to see is actually a new release of drivers that will land February-ish, that will take the next step in making it easier to use causal clustering. So, for example, the drivers are going to start handling some of the details around bookmarking. So, as a developer, you can just simply say, I want to read my own writes, and the drivers will take care of that. And then along those lines, there are, as Alistair mentioned, clustering, causal clustering is a foundation for all sorts of new things that we want to build into the clustering architecture. You'll start to see some of those next year, including additional features around multi-data center type scenarios and various other specialized uses. On the security front, Igor mentioned Kerberos as being something that's going to be supported in the first half. 3.1 includes a pluggable security architecture that was designed to enable things like Kerberos, and there are also various customer uses for it. And two other areas that I'll highlight are closing the gap between Cypher performance and the low-level API that you can gain access to via procedures. You can look at some great performance improvements that we have in store for making Cypher even faster. And then finally, another area is around just getting data into the graph. As data continues to grow, you can never be fast enough in terms of getting data in all sorts of modes. Jim mentioned 1 million writes per second. That's the bulk importer, which is for getting your initial data set created. And we also have some, we plan on bringing the transactional performance much closer to that. So you'll start to get much better insert, delete, update performance with the changes we have in store for next year.
Great. Sounds like it'll be an exciting year for engineering. Great. So our next question, we've seen that Neo4j is used in many different industries and across lots of different use cases. What are some industries and use cases that we're seeing Neo4j being used for right now that we're most excited about? Maybe new use cases, new industries. Let's go back to Emil for this one.
I got that one? Sweet. Good question. Well, so personally, I think that, the Panama Papers thing that happened this year was super exciting, I think, to all of us internally at Neo. Our mission is help the world to make sense of data, help the world to make sense of data, and I think this is a fantastic example of this, where we enabled, hundreds of journalists through 3 developers, right? 3 developers to take this massive data set and make sense of it, right? And they're on record as saying that, they couldn't have done it without Neo4j, and I think that's pretty amazing. In a similar vein, I know of at least 5, it's probably more, of separate projects and groups that are used in Neo4j in various ways for cancer research. And I think at this point probably everyone knows someone directly or indirectly, right, who's in some way, shape, or form been interacted with cancer, right? And that's a horrible thing. And I think the fact that we can be a small part of that, I think, is pretty cool. So those are 2 areas. I think this wasn't the question, but I'll use this opportunity anyway. I think one area where I'm hoping to see use of Neo4j is, there's been a lot of, political discussion this year, and I'm not going to open up that can of worm, other than saying that I'm personally, quite concerned about the entire fake news phenomena, right? Where it's been, I think, proven that, society now is not awesome at fact-checking all kinds of news. And I think there's an opportunity to write a PageRank equivalent for the detection of fake news. I think graphs is an amazing application for that. My gut feeling is that it may not be the toughest thing to do, but no one has done it yet. So if anyone out there feels like that's a worthy goal, I would love to see our technology being used for that. Which I know wasn't the question, but I wanted to say that anyway.
That's great. That sounds really interesting. Yeah, graph certainly seems to be a good data model for that use case. That's great. So another question that we have here, this one might be best for Jim here. So in the past few years, we've seen several new graph projects come about, not just databases, but also graph processing frameworks like Spark with GraphX and graph frames, and also visualization frameworks. Can you speak a little bit about how Neo4j compares to some of these new projects and how Neo4j fits in among them in the ecosystem?
Okay, yeah, absolutely. So look, Neo4j is absolutely best in class at graph storage and query. That's what we do. That's what the database stuff does. There are these other kind of allied tools and projects around viz and around processing and so on that are trying to do something to the side of Neo4j. So if you look at something like Spark and GraphX and so on, that's about graph processing. And of course, the kind of analog is that, if you were in ye olde world on Oracle or something, you wouldn't try and cram everything into your SQL statements. You'd have some external way. For the storage and query stuff, you'd write your SQL, but you'd have some other things that we used to call programs that would interact with the database out here. I think we're seeing something very, very similar to that. We've got technology that's aligned around graph for storage and query. We've got technology that's aligned around graph for processing graph, potentially in parallel. We've got technology that's aligned around graph for visualizing either the results of queries or the results of graph processing and translating it into some, hopefully business or domain-specific meaningful way. I actually think that probably the question's better directed towards Philip because I know that he explores these things. So I have a fairly kind of engineering view on that. But Philip, I guess you probably interject as well at this point.
Yeah, I just to add the Neo4j's core. Whenever we have an engineering decision to make or product decision to make around optimizing for transactions versus optimizing for bulk kinds of scanning or iterative graph operations, we've generally leaned in favor of optimizing for high volume transactional kinds of workloads. So you can look at Neo4j as being the best technology for the job for those kinds of problems, and something like like GraphX, Giraffe, Flink is being great technologies, not at all optimized for the transactions, but optimized for large iterative graph algorithms. Neo4j can make a great source of truth, though, for data that needs to be persisted. And there's a great Spark connector that's out there that I know many of you have used. That's a good way to pull data out of Neo4j, selected data, run a Spark algorithm over it, and then maybe enhance the data, like add relationship weights in the PageRank scenario, or just return your results and then not write back to the graph. So I think the two work together well hand in hand. And of course, Neo4j is good at certain kinds of global graph operations. I mentioned optimizations around doing counts of like labels and global counts through Cypher, and we've seen some interesting results lately from using Neo4j versus really any other technology, where you get the results of a global count by label in milliseconds, actually sub-millisecond, because it's just querying this up to the last ACID transaction statistics store inside of the database. So, so my advice would be, if you have a global operation, try running it on Neo4j. Try using Cypher, try using some of the procedures that are out there, and then if that operation, usually because it's highly iterative and it involves massive amounts of a massive subset of your graph, of a large graph, then look at using the Spark connector.
Okay. Really, that's okay.
Please.
So I think it's really, I mean, from our perspective, the fact that there's a rich ecosystem emerging around graph technologies, I think is so amazing, right? I mean, I don't think any single company can ever produce everything in a particular space, nor do I think that's even healthy. Even if it's possible, it's not healthy. So I think that's awesome for us to see. Our focus here, and sorry if I'm stealing your thunder here, Alistair, but our focus here really is, we believe that Cypher should be the lingua franca between all of these tools and technologies, right? Which is why we created the Open Cypher project. We believe, you know, maybe we're drinking too much of our own Kool-Aid, but like, we believe Cypher is magical, right? And there's been so many times when we've seen people going from imperative APIs to Cypher, and they get a 10x order, type improvement in terms of productivity. We think it's the best way you can speak graphs that at least we've been able to invent. And that's why we're giving it away freely, right? And so our goal really is that over time, that while we hope that many, many companies are going to contribute to the graph space, our hope is that we're all going to converge on this one language for interchange concept.
Right, that's great. Great, good point. So I know we're very much out of time here. Let's go ahead and take one more question for the group here. And a question from the audience: how does causal clustering setup play with Docker and other container orchestration tools like Swarm and Mesos? Igor, would you care to answer this one?
Sure. So we've been part of the Docker community ever since. I think maybe even 2 or more years ago, we've been publishing Neo4j images on Docker Hub. I've been this year to DockerCon, and we've been part of the Docker Store launch. Neo4j was only one of a handful, software providers and publishers there. So even for this 3.1 release, Docker image is usually available one day after we release. So images like that we just seen last week from community project that now Neo4j is available on as a universal package on DCOS Mesosphere. So that's working well. Our customers are choosing to deploy Neo on AWS and on Azure. We have AWS images, things like that. So we are present there where our customers wants us and where our customers are using us. As far as the orchestration is concerned, internally we are already testing how this service discovery works with technologies like Kubernetes and Swarm. So this is something which is in progress, but internally in our lab we already have it working with Swarm. So this is definitely an area where we will be pushing forward. Just another example that our community just issued a pull request to kind of like merge with our code. Is a simple improvement to our Docker image where you are able to set up environment variable to configure particular settings, so you can truly use Neo4j in a Docker image as a black box, and you just manage it through the environment variables. You don't have to touch this image. And we are like merging all of these, nice contributions for community, and we are improving this so you can truly be, using these packages and then orchestration frameworks to run Neo in the cloud on these environments.
Okay, great, thank you.
So a lot of good progress there.
Great, yeah, I know that containerization is really a helpful tool. A lot of the tools that my team works on uses Neo4j and Docker as well. Great. Well, that's more than the time we budgeted. So thanks everyone for staying over. I just want to say thank you very much to all of our panelists today for speaking with us and joining us. And as Jim mentioned, Neo4j 3.1 is now available for download. So please go ahead and try that out. We're really excited for you to experience some of the cool new features that we've been working on. And so thank you very much for joining us. We will be sending out slides and video recording later. So thanks, everyone.